The next topic is inverse matrices. A square matrix A is invertible. So square means the dimensions have to match, right? So if I've been calling matrices m by n, so m rows and n columns. Square just means that m is equal to n. So I could say it's either m by m or n by n. And I think most of the time I'll say n by n. So A is invertible if there exists a matrix. So I'm going to call the inverse A to the minus 1 power. It doesn't mean 1 over A, but it's sort of in the same sense that if I had a real number that's not equal to 0, and I took 1 divided by that real number, then when I multiplied those two things together, I would get 1. So A inverse is going to be a matrix where I multiply either before or after A. So I can take A inverse A, that has to be equal to the identity matrix, and A inverse has to be equal to the identity matrix. If I can find this matrix A inverse, then I will say that A is invertible. So the inverse, if it exists, is unique. And one way you can see that is if So what I'm trying to do here is I'm trying to say that B and C are two different matrices that satisfy the properties in the definition. So the left-hand inverse, this one here, will be the matrix B, B, and the right-hand inverse will be this matrix C. And then you can do a clever little trick. So if I have B times AC, but what is AC? That's just the identity matrix. So this is B times the identity matrix, which is just equal to B. But since I know AC, the product AC is also equal to the identity matrix, then I can substitute the value AC in here for I. And then for my rules of matrix multiplication, it doesn't matter where I put the parentheses. So I'm going to, instead of putting the parentheses around AC, I'll put the parentheses around BA. But I've already assumed that this is equal to the identity matrix. So this is telling me that this is I times C, which is the same thing as C. So if I assume BA is equal to the identity matrix and AC is equal to the identity matrix, then you can make an argument like this to say that B has to be equal to C. So there can only be one matrix that satisfies this property, or these two properties, if an inverse exists. So if A is invertible, then the unique solution to this system of equations represented by AX equals B. So I'll start off just by writing AX equals B. If A is invertible, then I have this matrix A inverse. So I'm going to multiply both sides of this pre-multiply by A inverse. So I put A inverse before the AX and an A inverse before the B. And then A inverse A, by the definition of the inverse, that's just the identity matrix. So identity matrix times X is equal to X. So I end up with X, which is the solution, this is the thing I'm looking for, is equal to A inverse times B. And if there's a vector X that's not equal to 0, but that has the property that A times X is equal to 0, then A is not invertible. And basically, I want to use this result here just to show what's going to go wrong. So this is a kind of common argument that you make in mathematics. I want to assume that X is not equal to 0. And then based on that assumption, I want to prove that it is equal to 0. And so I'm assuming something is true, contradicting that assumption. And so that's going to be called a proof by contradiction. And that's going to allow me to say that A is not invertible. because if A is invertible, I can solve for this vector x here using this trick that I've just done in the third bullet point. So if there is a vector, a non-zero vector x, so at least one element of this vector x has to be non-zero, then I could write x as the identity matrix times x. And then if A was invertible, it would have an inverse, and that would satisfy the first property in the definition. So I could replace this identity matrix with A inverse A. And then I can just, because of my rules for matrix multiplication, I can put parentheses wherever I want to. So I'm going to put some around this AX here. But I've assumed that there's this non-zero vector x that has a property that AX is equal to 0. So x, remember, is non-zero, has at least one non-zero component. But I can replace this AX with the 0 vector. And so that tells me that x has to be equal to A inverse times 0, but anything times 0 is equal to 0. So what I've assumed on the left is that if A is invertible, or I've assumed on the left that I have an invertible matrix A and this non-zero vector x. And then I've showed that A inverse times, well, so essentially what I've been able to show with that assumption is that my non-zero x is equal to 0. So that's a contradiction. So I can't have a non-zero vector x having every element equal to 0. And so then whatever I assumed has to be false. So I can't assume that A is invertible. Or if I assume that A is invertible, I can prove that it's not invertible, essentially. So that's how you show that if there is this non-zero vector x that satisfies AX equal to 0, then A is not invertible. In the 2 by 2 case, there's actually a nice formula for computing the inverse. So a 2 by 2 matrix will be invertible if and only if AD minus BC, so I'm just labeling the elements. So I have A, B, C, D as so AB is the first row, CD is the second row. And it needs to satisfy this property. So the AD minus BC has to be non-zero. If that's not equal to 0, then the inverse of A is going to be equal to 1 divided by AD minus BC. So this is why this value has to be non-zero, because I'm going to divide by it. Times D minus B minus CA. So that's going to give me a matrix that when I multiply it either in front of or after A is going to give me the identity matrix. And the number AD minus BC is called the determinant of A. So essentially if this number is not equal to 0, then A is going to be invertible. So a matrix is invertible if its determinant is not equal to 0. And then just as a special case, I want to point out the easiest type of matrix to compute the inverse of. So that 2 by 2, I have this nice formula here. Not nice necessarily, but I have a formula. A diagonal matrix just means that any off-diagonal element, so any element where I is not equal to j, so above the diagonal or below the diagonal, all of those have to be 0. If I have a matrix like that, then the inverse is just 1 over the diagonal elements. And so this also supposes, so A inverse will exist if all of these diagonal elements are non-zero. If one of these, so suppose the first one was equal to 0, then there's nothing I could put in this cell here, so that matrix wouldn't have an inverse. So if the diagonal elements of a diagonal matrix are all non-zero, then I can very easily calculate the inverse just by taking the reciprocal of each diagonal element.
What happens with the other term?
All of the rest of them stay 0. Yeah. And you can just convince yourself of this. When you do the multiplication, I'll have first row times the first column here. So I'd have d1 times 1 over d1, and then just a whole bunch of zeros here times a whole bunch of zeros here. And if the I is not equal to j, then the non-zero element here will just crash into a 0 on this side, and the non-zero element here will hit a 0 element on this side. So everything ends up being 0 off the diagonal. So I get the identity matrix back. So then we have some rules for inverses. So these are probably the most important things you're going to want to remember about the inverse. Generally, if you ever need to compute the inverse of a matrix, you're going to do that using a computer. So even this formula here, it's not something I have committed to memory. If I need it, I look it up. Or it's usually, if you remember just the determinant, you can figure out what the arrangement of the rest of the letters has to be pretty quickly. What is useful, though, is thinking about matrices sort of more abstractly. So instead of thinking about the actual elements, I'm trying to do mathematics with the matrices themselves. And so if I end up with a product AB, and I need to take the inverse of that product, that ends up being B inverse times A inverse. And the way to convince yourself that's true is just to plug that into the definition of the inverse. So remember, my definition of the inverse said that if I have the inverse times the matrix, that has to give me the identity. So in this case, it would be AB inverse times the matrix product AB. And now this I can write without the parentheses, and that'll be the same thing. The AB inverse, the order swaps, so it becomes B inverse A inverse. And then I'll put some parentheses around what I get on the inside. A inverse A is just equal to the identity matrix. So it's going to just sort of collapse in upon itself. So this I can multiply that, I times B. That's identity matrix times anything, just gives me the anything back. So I times B gives me B back. I end up with B inverse B, which is, by the definition of an inverse, the identity matrix. And then I can do the same thing for the right-hand inverse. Again, because it switches the order, all that's going to happen is I end up eliminating the B first. So the B multiplied by B inverse becomes identity. And I end up with AIA, or AIA inverse, which becomes AA inverse, which becomes I. And you can do exactly the same thing for longer products as well. So if I have ABC inverse, I just reverse the order of the product, so that becomes C inverse B inverse A inverse. And if you wanted to prove that that's true, you would just put an ABC over here, and then it's going to collapse 3 times rather than just 2 times. But what you're left with is the identity matrix. So now let's think about how would I actually find A inverse. So I need to find a matrix so that when I multiply A by A inverse, I get the identity matrix. If I can find this, I've already argued that it's going to be unique, and it'll also be the matrix that can go on the front. So I don't need to compute both of them. I just need to compute one of them. If there's one matrix that has this property, then it automatically has the property that if I pre-multiply by A inverse, that's also going to turn A into the identity matrix. So let's make some vectors here. So I've used E before to mean a column vector of all ones. I'm going to add a subscript now to mean it's a vector of all zeros, except it's got a 1 in whatever position this little subscript corresponds to. So E sub 1 would be 1, 0, 0. And if it's in general in n dimensions, then I have E1 up through En. And it just means it's all 0 except for the ith element, and that's going to be equal to 1. So then I have E2 is 0, 1, 0, and E3 is 0, 0, 1. And then if I bind all 3 of these vectors together, E1, E2, E3, that's just going to be the identity matrix. So you can almost kind of see it here. I just have 1s going down the diagonal. And now I can imagine that I have an inverse, so A inverse, an inverse of this matrix A. And the columns of my matrix A inverse, I'm going to call x1, x2, and x3. So x1 is a column vector with 3 entries, x2 is a column vector with 3 entries, and x3 is a column vector with 3 entries. So I can write out my A inverse is equal to A times these 3 column vectors bound together into a matrix. And I know that has to equal E1, E2, E3, which is the identity matrix. And so what I end up having to do is solve 3 systems of equations. I have to solve AX1 equals E1, AX2 equals E2, and AX3 equals E3. So if I was actually computing the inverse, remember before I said I could compute the solution to AX equals B by pre-multiplying by A inverse. So if I already knew what the inverse was, I could just multiply and find that, well, A inverse B is going to be the solution. But if I just want to actually solve that system, I would just be solving one of these. If I want to find A inverse and then use A inverse to solve that system, I end up solving 3 of these. So it ends up being 3 times as much work to find A inverse to solve that problem as it would be just to directly solve that problem using elimination. So computing A inverse, 3 times as much work as solving AX equals B. So this is going to be sort of one of the morals of the story here, is quite often if you need to compute an inverse, if you see an inverse in a matrix formula, there's a better, faster way to solve the problem without using an inverse. So in this case, I was looking at a 3 by 3 case. And I said that you'd have to solve this 3 times. It turns out that if you look at a 4 by 4 case or a 5 by 5 case, the 3 times ends up being an upper bound on the amount of work you have to do, because you've done enough elimination on A in solving these first 3 that you can kind of recycle that, if you are intelligent about the algorithm you use. And so the algorithm is called the Gauss-Jordan method, which I'm not going to go through this here, but it's essentially just doing this elimination problem. And you can do this in n cubed elimination steps. But if you compare that to solving AX equals B, this requires n cubed divided by 3, or roughly n cubed divided by 3 elimination steps. So you're going to be doing less work. Sorry, not n cubed, this is not quite right, not elimination steps, but mathematical operations. But the point I want you to take away from this is it's 1/3 as much work to solve AX equals B using elimination as it would be to find an inverse and then use that to solve AX equals B. And now remember, I said if I was doing elimination and I ran into a row that was all zeros, I couldn't find a pivot in that row. So that particular system does not have a full set of pivots. Oops. And now I have this idea of invertibility. It says some matrices have inverses and some matrices don't. So if a matrix has an inverse, then I can't find a non-zero vector that has the property that if I say A times that vector, I get 0. And so it turns out these 2 things are related. So let's suppose A is a square matrix. And suppose there are n pivots. Then I could solve each one of these equations, and that would give me these xi's that would be the columns of my inverse. So I can put these column vectors xi together to make a matrix that's the inverse of my matrix A. And so elimination then gives a complete test for A inverse to exist. So there has to be n pivots. So this isn't a complete proof. This is just the result. So in a linear algebra textbook, they will tell you exactly how to do this, because it's sort of something you have to do both directions. But essentially, if a matrix A is invertible, then you can find a set of n pivots. So you say it has a full set of pivots. And if a matrix is non-singular, that means every row has a pivot, then that matrix is also going to be invertible.